To really understand body fluids, you need to understand how water distributes itself in the body. It does so due to the process of osmosis. Essentially, solvent moves from where the solute is in low concentration to where it is in high concentration. With this in mind, I will also explore osmotherapy with mannitol.
Tutorial 3, Osmosis. Previously I discussed atomic weights and molecular mass, molality in grams percent, salts, ion and ion distribution, the electrolyte content of intravenous fluids and how to calculate them, and we did a supplementary tutorial on calcium replacement fluids. This time I will discuss the principle of osmosis, the distribution of water and solute in the body, and osmotherapy. Let's start with a clinical scenario. You're called to the emergency department as there has been an accident. A young man, Brian, has been struck by a car and has been brought into the ED with a traumatic brain injury. When you see him, he's unconscious and his brain scan, the CT of his brain, shows significant cerebral edema. You're advised by the neurosurgeon to administer 1 gram per kilogram of mannitol, and Brian weighs about 80 kilograms. Why do you administer mannitol to brain-injured patients, and how do you dose 20% mannitol, and what is the goal of therapy? Well, it starts really with the concept of osmosis. Water is freely permeable across cell membranes. It is constrained by the solute concentration on either side of the membrane. In this case, the solute concentration is constant, so there is no movement of water. Water moves across the solute concentration gradient from high concentration to low concentration. In this example, there are more particles on the left-hand side of the membrane. The concentration is higher there. Consequently, water moves across the membrane. This continues until the concentrations are equal, and that process is known as osmosis. Osmotic pressure is the force in centimeters of water required to prevent fluid movement across an osmotic gradient. In this example, the concentration remains greater on the left-hand side and water is restrained from moving by an osmotic pressure. Osmolality. Dissolved particles, solute, impart and affect osmosis on the solvent. Osmolality is related to the number of solute particles per kilogram of solute, in this case, in the human body, water. It's all about the number of particles, not their size, not their charge. Large molecules such as glucose, urea or ethanol, and single ions such as sodium and chloride have the same osmotic effect. For non-dissociating substances, 1 mole equals 1 osmol, and 1 millimole equals 1 milliosmol. So 6 millimoles of glucose equals 6 milliosmoles. But dissociating substances behave differently. NaCl, salt, breaks down into sodium and chloride. 1 mole of NaCl equals 1 mole of sodium and 1 mole of chloride. They are 2 separate moles and have the effect of 2 osmoles. Extracellular osmolality is between 290 and 300 milliosmoles per kilogram of water. 1 milliosmol of substance decreases the activity of water by 17 millimeters of mercury. So if the ECF osmolality is 300, then 300 times 17 is 5100 millimeters of mercury. This is the osmotic pressure of most body fluids, as extracellular and intracellular osmolality are usually the same. One way of looking at body fluids is that 1/3 of body water is extracellular and 2/3 of body water is intracellular. But also 1/3 of osmotically active solute is extracellular and 2/3 of osmotically active solute is intracellular. If you know the plasma osmolality, then you know the intracellular osmolality, because osmolality equalizes between the intracellular space and the extracellular space. And that also means that the interstitial osmolality must equal the intravascular osmolality, or the plasma osmolality. Extracellular water loss leads to cellular dehydration. So if there's water loss on the left-hand side, then water will move from the intracellular space to the extracellular space. In the operating room, patients lose a lot of water by evaporation, and so they do need water to replace this intercellular fluid loss. Let's move on to osmotherapy. Osmotherapy involves using solutions with different osmolalities to change the fluid volumes in different compartments. So this is a picture of the blood-brain barrier. These are astrocytes here, and these are brain capillaries here. There is no paracellular transport of solutes. They must travel through the cells. Water is freely permeable across the cells, and it can move across determined by the osmotic gradient. Returning to this cartoon, what's happened to Brian is that he's had a traumatic brain injury, and that has caused the collection of cerebral edema in his brain, and now his brain is swollen and he's at risk of brainstem herniation. Now what we're going to give Brian is Mannitol, which is an osmotically active agent that is biologically inert, and that what that's going to do is introduce a lot of additional osmoles into the extracellular space. As a consequence, now there are more particles on the extracellular side of the blood-brain barrier of that cell membrane, and as a consequence, water will move from the brain into the extracellular space, and then of course will be lost by urination. You check two things here: the urinary output, which should be quite dramatic, and the plasma osmolality. The goal is a brisk diuresis and a rise in the plasma osmolality to between 310 and 320 milliosmoles, keeping the osmol gap to less than about 20 milliosmoles. So in terms of Brian and his 1 gram per kilo of mannitol, this is 20% mannitol. How much is in this and how many milliosmoles are you going to administer? Let's work the problem. 20% mannitol is 20 grams per 100 mils, and 1 gram is 5 mils. 1 gram per kilo is 80 grams or 400 mils. The molecular mass of mannitol is 182 grams per mole, and 1 mole of mannitol is 182 grams. 1 gram of mannitol is 1000 divided by 182, or 5.5 moles per gram. 80 grams or 400 mils is 80 times 5.5, or 440 millimoles, which works out as 440 milliosmoles. So you're essentially administering 5.5 millimoles per kilogram when you're giving a gram per kilogram. Now there are a couple of different formulations of mannitol. 20% mannitol, 200 grams per 1000 mils, 1 gram in 5 mils, 1.098 millimoles per mil, or 1.098 milliosmoles per mil, or 1098 milliosmoles per litre. There's also a 10% version, which is 100 grams in 1000 mils. 1 gram is 10 mils. Because of the molecular weight being 182, there are 0.55 millimoles per mil, or 0.55 milliosmoles per mil, or 549 milliosmoles per litre. What's the deal with the osmolality of 320? The normal plasma osmolality is approximately 300 milliosmoles per litre. The normal extracellular fluid volume for an 80 kilogram male is about 15 litres. So if you look at 15 times 300, you end up with 4,500 milliosmoles in the extracellular space. 400 mils of mannitol, 20%, adds 400 mils to the extracellular fluid and 440 milliosmoles. If given as a quick bolus, we now have 4,940 milliosmoles in 15.4 litres, which works out at 4,940 divided by 15.4 or 320 milliosmoles per litre. Let's review this tutorial. In this tutorial I've covered the principle of osmosis, the distribution of water and solute in the body, osmotic pressure and osmotherapy with mannitol. Next time I will discuss the calculation and measurement of plasma osmolarity and osmolality, the concept of the osmol gap, and the tonicity of fluids.
Well, that was a short tutorial on osmosis. It sets the stage for looking at iso, hypo, and hypertonic fluid in the next tutorial.